about the exciting subject of aircraft hardware, meaning basically bolts and nuts. Now, as far as aircraft bolts are concerned, most bolts that are used in aircraft structures are either general purpose AN, Air Force Navy, or NAS, National Aircraft Standard, close tolerance bolts. Those are the two types that we normally use in aircraft structures. Now, as far as the bolts are concerned, bolts are identified by the code markings on the heads of the bolts. And the FAA is going to ask you to know some of those. For instance, take a look at the FAA figure pages at figure 42, which has 3 different bolt heads shown. The FAA might ask you, which of these bolt heads would you see for an AN standard steel bolt? Well, an AN standard steel bolt is identified with a cross or asterisk on the bolt head, and the one that looks like that is illustration 1. There's our cross on the bolt head. That would be an AN standard steel bolt. They might say to you instead, which one of these bolt heads would be an NAS close tolerance bolt? Well, an NAS close tolerance bolt is indicated with an X inside a triangle on the head of the bolt. And the bolt head that looks like that is number 2. There's the triangle with the X or cross inside it. And that will be an NAS close tolerance bolt. Or they might say to you, which of these bolt heads, not too many choices left, identifies a corrosion-resistant AN standard steel bolt. In that case, what you're looking for is a single raised dash on the head of the bolt, and that is bolt head number 3, a corrosion-resistant AN standard steel bolt. Let's talk now about clevis bolts. Now, with a clevis bolt, the head of a clevis bolt is round, and the head is either slotted to receive a common screwdriver like this one is, or it's recessed to receive a cross-point screwdriver. Take a look at figure 43. The FAA might give you this and say, okay, we want to know which of these illustrations, 1, 2, or 3, is a clevis bolt. And the only one that has a round head on it is which one? Illustration number 3, and that means number 3 is the clevis bolt. Okay, talking about clevis bolts, how are they used? They're only used for shear load applications, and they are never used in tension applications. Never in tension applications, just for shear loads. Now, if you have a clevis bolt that's used with a fork end cable terminal, the way you secure it is with a shear nut tightened to a snug fit, but no strain imposed on the fork, and then you safety it with a cotter pin. Now, talking about bolts, let's talk about the grip length of a bolt. The grip length is the unthreaded portion of the bolt, and of course it's going to vary depending on the type and the purpose of the particular bolt. Bolt grip lengths, the FAA says, should be equal to the thickness of the material through which they extend. So the grip length, the unthreaded portion in general, should be equal to the thickness of the material through which they're going to extend. So suppose the FAA asks you to determine the grip length on a particular bolt, and they give you this information about the bolt. The overall length is 1.5 inches, the shank length is 1 3/16 inches, and the threaded length is 5/8 of an inch. Well, first of all, the overall length doesn't matter to you at all. What you're interested in is the shank length and the threaded length. The shank length includes both the threaded and non-threaded portions, and of course the non-threaded portion is the grip length. So we just have to subtract those two in order to determine the grip length. We are given a shank length of 1 3/16 inches. From that, we subtract the threaded portion, which we were given as 5/8. Convert both of those into 1/16 of an inch in order to be able to work with them easily. 1 3/16 of an inch is the same as 19/16. 5/8 is the same as 10/16 of an inch, and then you simply subtract them. 10 from 19 gives you a grip length of 9/16 of an inch. But the problem is, the FAA answer is not in a fraction 9/16. They want to know in decimals. So what you do on a calculator is you simply divide the 9 by the 16, and that will give you 0.5625, which is the length of the non-threaded portion of the bolt, the grip length on that particular bolt. Now let's talk about the threads on bolts. The class of a thread indicates the clearance allowed, the tolerance allowed in manufacturing. Basically, whether the nut can be turned with the fingers or whether it requires a wrench to tighten it. Class 1 is a loose fit. Class 2 is a free fit, Class 3 is a medium fit, and Class 4 is a close fit. So which one do you normally have for aircraft bolts? Class 3, the medium fit, is what aircraft bolts are usually manufactured with. And you need to know that. You need to know the Class 3 for the FAA written exam. Now, let's take a look at a fiber type lock nut. When you have a fiber type lock nut, the locking feature of it is obtained by using an unthreaded fiber locking insert. So inside the nut there is fiber insert, and it is not threaded, so when the bolt goes into it, then it tightens up, and that provides the lock nut feature. The fiber type locking nut should never be used on an aircraft if either the bolt or the nut is subject to rotation, because it won't hold the way you want it to. Never use it if either the bolt or the nut is subject to rotation. Now, when you're installing nuts and bolts, where do you look to find the standards for how much the bolt, studs, and screws should protrude through self-locking nuts? Well, you'll find it in Advisory Circular 43.13-1B, Acceptable Methods, Techniques, and Practices for Aircraft Inspection and Repair. You need to know the number of that advisory circular well, because you'll refer to it often in your career. Now, do not confuse this advisory circular, 43.13-1B, with another similar sounding one, 43.13-2A. That advisory circular, -2A, tells you about aircraft alterations. You also will not find general standards, such as how far a bolt should protrude through a self-locking nut, in places like aircraft specifications or type certificate data sheets. Those documents are specific to an aircraft type and don't have that kind of detail. What's important here is where you find those standards for details such as the protrusions of bolt, studs, and screws through self-locking nuts, and you find them in this advisory circular 43.13-1B. Now, unless it's already specified or required, the way you install aircraft bolts is so that the bolt head is upward or in the forward direction. That way, if the nut comes off, you still got a pretty good chance that the bolt's going to stay in position. So the bolt head should be upward or in the forward as opposed to a rearward position. Now, unless they specify otherwise, the torque values for aircraft nuts and bolts relates to dry, clean threads. That means the threads must be free of any grease and any oil. So dry and clean threads is what you need to have when you're working to torque down the bolt. Now, if the specific torque value for nuts is not given, the recommended torque values can be found, guess where? That same advisory circular we were just talking about, Advisory Circular 43.13-1B. So if they do not give you the recommended torque values, you can find them in this advisory circular. Now, let's assume that you're using an aircraft bolt and a castellated tension nut in order to attach a particular component to the aircraft structure. What happens if the cotter pin hole is not aligned within the recommended torque range? What should you do about it? Well, the acceptable practice is to change washers and try it again. And that's what you need to know about the nuts and bolts of aircraft hardware.
Let you and I talk about some things they ask you on a general exam about physics. And by the way, don't panic, because the things they ask you about physics on the general exam are very simple and very basic. This is not going to be complicated. For instance, they ask you about temperature, and they say, what is temperature a measure of? And the answer is, temperature is a measure of the kinetic energy of molecules. What is kinetic energy? That's the energy of motion. It's stored energy. Give you an example. A car is going down the road. It has stored energy. It hits a tree. It gives up that energy. You put on the brakes. You heat up the brakes because you're giving up the stored kinetic energy. Well, molecules in a container, these are air molecules, for instance, in a container, are constantly moving around. If you increase the temperature, they move faster. So you can see that these moving molecules are a way of storing kinetic energy. So therefore, temperature is a measure of the kinetic energy of the molecules of any substance. They're also going to ask you on the test, how do you transfer heat? Well, we're asking how you get heat from one space to another space, one place to another place. Well, there's three ways you can transfer heat. Heat can be transferred by convection. If you have hot air rises. That's an example of convection, and it's a transfer of heat from one place to another place by convection. Another way you can transfer heat is by conduction. If you have a hot spot on a stove, the rest of the stove will get hot because conduction conducts the heat from one place on the stove to another place. That's from one molecule heating another molecule. That's conduction. And finally, heat may be transferred by radiation. The sun shines down, heats up the ground. That's called radiant heat as the ground heats up. And radiation can heat up the ground without heating the air that it went through. That's one of the properties of radiation. And that is three ways that heat may be transferred: by convection, conduction, and radiation. Now, one of the things you need to know on the test is here is one way that heat cannot be transferred, and that is by diffusion. Diffusion is mixing of molecules. If you have a container of air and you introduce some other gas in there, they will mix together. That is diffusion. If you pour two liquids together in a container, they will mix up perfectly in that container. That is an example of diffusion. That is not a way of transferring heat. That's a totally different concept. They're going to try and confuse you with that on the FAA written exam. Here are the three ways that heat may be transferred: convection, conduction, and radiation, but heat may not be transferred by diffusion. Now, they also ask you some questions on the test about the pressure of a gas in a confined container. They're going to say, what's going to determine that pressure? Well, that pressure will be determined by the temperature and volume, and there's a law about this, and that law is called Boyle's law. So they're saying that the pressure of a confined gas is determined by the relationship or the ratio of temperature to volume, temperature divided by volume. So you can see as the temperature increases, the pressure would increase. And as the volume increases, then the pressure would decrease because you're divided by the volume. Now, here's the way they're going to ask you a question about this. They say you have a confined gas, and the temperature of that gas stays the same, and the volume of that gas, the volume of the container that it's contained in, doubles. What would happen to the pressure? Well, if the temperature stays the same and the volume doubles, you can see the pressure would be less. All right, another way they're going to ask the same question is, you take both the volume and the temperature of the gas and double them. You take both the volume and the temperature of the gas and double them, what would happen to the pressure? Well, the pressure is the relationship or the ratio of temperature to volume, and if they both double, the ratio would stay the same and pressure would stay the same. So what you need to know is if both the volume and the absolute temperature of a confined gas are doubled, the pressure will not change. How about that? This time, let's you and I take a look at a liquid. And the thing you need to know about a liquid is that a liquid is not compressible. You cannot compress a liquid. That's the principle that hydraulic systems work on. Instead of compressing, the hydraulic system moves things out of the way. You can't compress a liquid. So if you have a confined container and you keep pumping more stuff into a container and it's got liquid in it, the pressure is going to increase dramatically. So you have a confined container, keep the temperature the same, and put more liquid in that container, you're going to have a huge immediate increase in pressure because the liquid is not compressible. They're kind of a backwards question they ask you about this. Let's take a look at the backwards question about this. The question says, the temperature of a confined liquid is held constant and its pressure is tripled. What will happen to the volume? Well, this is kind of backwards, but what they want you to know is the volume will remain the same. And essentially what they're saying is a liquid does not compress. You cannot change the volume of a liquid even if you increase the pressure. The volume of that liquid will not change. All right, let's take a look at another question they're going to ask you about a liquid. And they say you have a given liquid. When will it boil? Well, the boiling point of a given liquid varies with the pressure. You have a pail of water down here, and take that water up in the mountains and try and boil it, you'll find that the temperature that it boils will be much lower temperature because the air pressure is less. And if you take it down to sea level or even below sea level, then the boiling point will be higher because it varies with the atmospheric pressure that's on it. Now here is an example of big iron. In fact, if you look at this, this is an example of fast iron because this is an F-14 Tomcat. You could swing those wings back and you can hustle in that sucker, and they're going to ask you a question on a test about the speed of sound, and it's pertinent when you're talking about an airplane like this, I tell you that. They're going to ask you, what does the speed of sound vary with? What could change in the atmosphere to change the speed of sound? And the answer is the speed of sound changes with a change in temperature. So with an airplane like this, if you're flying it, you should know that if things cool down, your true airspeed might stay the same, but your speed relative to the speed of sound will change because the temperature changed. All right, now let's talk about humidity. They're going to ask you about water vapor in the air. And water vapor, of course, is vapor that is not visible. Clouds are visible moisture, but when we're talking about water vapor, we're talking about water that has actually gone into the air. And so they're saying on the test, all right, super mechanic, what is absolute humidity? And absolute humidity is the actual amount of water vapor in the air, in the mixture of air and water. Now, then what's the difference between absolute humidity and relative humidity? Well, we're going to find out. Relative humidity is the ratio of water vapor to saturation. Now, let me put that the way they're going to put it on the FA written exam. Here's exact words for the FA written exam. Relative humidity is the ratio of the water vapor actually present in the atmosphere to the amount that would be present if the air were saturated at the prevailing temperature and pressure. So 50% relative humidity means the air at this pressure and temperature is holding 50% of the water that it could hold if it were saturated. They're also going to ask you about dew point. What is dew point? Well, dew point is the temperature to which the air must be at a constant pressure lowered to. You lower the temperature of the air to become saturated. So it's the temperature which the air must be reduced to have saturated air. And so on the test, it's going to go like this. Dew point is the temperature to which humid air must be cooled at constant pressure to become saturated. Now let's talk about the density of humid air. Is humid air more or less dense than dry air? And the answer is water vapor in the air is less dense, and humid air is actually lighter, less dense. So they're going to ask you a question about this on the test, and the answer is very, very easy. All you have to do is remember, anytime you have a mixture of air and water vapor, the more water vapor the mixture has, the less the mixture will weigh, because water vapor weighs less than dry air. So here you have 35 parts of dry air and 65 parts of water vapor. Would that weigh more or less than a 50-50 mixture? It would weigh less because you have more water vapor, 65 parts of water vapor, so this mixture would weigh less. So that's all you need to remember is the more water vapor, the less the mixture is going to weigh, and that'll answer any question they're going to ask you on the test. All right, now they're also going to ask you what is the effect of high temperature and high humidity on the landing speed of an aircraft given the same indicated airspeed on final. And the answer is the true landing speed of an aircraft is greatest at higher temperatures and higher humidities because the air is less dense. So even if you're flying at the same indicated airspeed on landing, if you increase the temperature, you increase the humidity, the true landing speed, the true speed through the air will be higher. Let's talk about that famous Swiss guy named Bernoulli. And Bernoulli studied fluid dynamics. And since air is also a fluid, Bernoulli studied aerodynamics at the same time. And he did a lot of interesting experiments and discovered some things that are very useful to us. So let's take a look at what Bernoulli did. First of all, Bernoulli put air through a tube, and we'll use air as an example. It could be any kind of fluid, but we're going to say air. Put air through a tube and measured the air pressure as it went through a tube. And he put a narrow spot in the tube. Now, if you think about this, you have air going in the tube, and the same amount of air has to come out the back of the tube. So if you put a narrow spot in the tube, the air has to speed up when it goes through that narrow spot. Now, what Bernoulli did that was interesting is he measured the air pressure as the air went through this tube. So here you have the pressure at the beginning of the tube, and at the narrow spot he had the pressure again. He measured the air pressure at that point. And what he found out that was so interesting is that the faster the fluid was going through this tube, or the air was going through this tube, the less the pressure was. So you'd have a pressure here, and you'd have less pressure when the air went through the narrow part of the tube. And he measured that and determined that scientifically, took notes, and everybody could repeat it. And so we know that as air goes through a narrow part in a tube, as the air speeds up, the air pressure becomes less. And that's Bernoulli's principle. Now, you can actually tell the rate of the air or fluid going through this tube by simply measuring the pressure differential. The greater pressure differential you have, the greater the rate of the fluid going through here. And that's one way you can indirectly measure the rate of flow through a tube, just measure this pressure differential. By the way, the pressure of the air coming in the front here would be the unmetered pressure. And when it goes through a narrow spot, it's being metered, so this would be the metered pressure in the narrow spot. So they're going to ask you a question, as you might guess, about this on a test. We're not doing this just for the fun of it. Let's take a look at the question they're going to ask you on the test. They're going to say, all right, you have three situations, A, B, and C, and you have an unmetered and metered pressure. And which one of these has the fastest rate of flow through the meter? Well, all you have to do is measure the difference between metered and unmetered, and the one with the greatest differential has the fastest rate of flow of that fluid. By the way, you can ignore atmospheric pressure because atmospheric pressure affects everything in exactly the same way. So you can ignore atmospheric pressure. It's on both sides of the equation here between metered and unmetered. So all you have to do is take the differential. Here the differential is 0.5, not much differential. Here the differential is 11, and here the differential is 12. So on C here, on 17 and 5, that differential is 12. That's the greatest differential between all of these, metered and unmetered. And the greatest differential between metered and unmetered pressure tells you that you have the fastest flow rate through that venturi. So let's go back and take a look at that venturi one more time. And you here have that venturi, and here is the metered pressure. When it's low and the unmetered is high, the greatest differential gives you the fastest flow rate. Now, anytime the air is forced to speed up, you'll have a decrease in pressure. So you could just have it going around a curve and do the same thing. You wouldn't even need the second half of this venturi. So let's get rid of the second half of this venturi and see what we have. And son of a gun, you might recognize this now. You have a wing. The air underneath the wing has a straight shot and is not very much disturbed, but the air over the top of the wing gets forced out of the way, and it therefore has to go faster. And by the way, air is incompressible. You can't compress free air. If you could trap it in a gallon jug, you might be able to compress it, but free air is incompressible, so it doesn't compress as it goes over the top of the wing. It just simply speeds up as it goes over the top of the wing there. So that's the principle upon which an airplane wing works. It's designed to produce lift, and it results from a relative positive pressure underneath the wing surface and negative pressure above the wing surface, and that's what creates lift. Now, if you increase the speed of the air going over this wing or the airfoil passing through the air, either way, you're going to increase lift because you'll have an increased differential. We always said the faster the fluid is going, the more differential there is. So if you increase the speed of this fluid, air in this case, going by this wing, you'll have more lift. Now, there is another factor about making lift that the FAA wants you to know about, and I think you'll see it right here. This is a wind tunnel with smoke flowing over an airfoil shape. And the thing I want you to notice is that the air at the top of the wing is actually being deflected downward, and the air at the bottom of the wing is being deflected downward. And this downward deflection of the air, you might hear some people call that a downwash. So there's a downwash. And if you go back to your science studies, dig out Newton's third law of motion, you'll probably remember for every action, there is an equal and opposite reaction. So in this case, the air is being deflected downward. That means there's an upward force on the wing, and that's part of what we call lift. So the FAA wants you to know that an airplane wing is designed to produce lift by having negative pressure above the wing, positive pressure below the wing, and a downward deflection of air. Now let's take a look at another concept they're going to ask you about a wing, and that is the aspect ratio of the wing. And an aspect ratio is the ratio between the wingspan, which is from wingtip to wingtip, to the chord, which is from front to back. Now, sometimes wings chords will change, so you can take the average chord. So the aspect ratio is actually the ratio between the wingspan, which is tip to tip, to the chord. Now, what kind of, and they call that the mean chord, by the way. That's the average chord, so we'll call it the mean chord. What kind of wings would have a high aspect ratio? Well, it's one that you want to be able to fly slowly. For instance, maybe a glider is a good example of a high aspect ratio wing, and that certainly is a high aspect ratio wing right there. A long, skinny wing has a high aspect ratio. Now, a wing with a very high aspect ratio like that in comparison with a low aspect ratio wing will have a low stall speed. So you can expect this glider, with everything else being equal, to have a lower stall speed. Now let's take a look at the plan form of a wing, and let's take a look at a question they're going to ask you about that. And by the way, the plan form of a wing is the view of the wing when seen from above. It gives you the general shape of the wing. And this is a rectangular wing plan form right here. And the question they're going to ask you about that is, what are the advantages of a rectangular wing plan form? Well, first of all, a rectangular wing has a tendency to stall at the wing root first, and that is a very, very good thing, because what happens is you still retain aileron control out here because you're not stalling at the tips, you're stalling at the root first. And at the same time, when the wing stalls at the root first, you now have a lot of aerodynamic warning of the stall, because this disturbed air comes back here and hits the tail and then shakes the wheel of the aircraft, and therefore it wakes the pilot up and says, "Hey dummy, this wing is about to stall." So a rectangular wing is a very good wing for low-time pilots, because it, one, gives you very good stall warning to let you know it's about to stall, and number two, gives you control throughout the stall right up to the last part of the stall. Now, if you want to make sure a wing stalls near the wing root first, you install this. It's called a stall strip. And at high angles of attack, this stall strip causes the air to burble here near the wing root first rather than out at the wing tip, and it creates the stall here first. So if you happen to be pre-flighting an aircraft or doing some work on it, and you notice that all or a significant part of this stall strip is missing, what's going to happen is the stall won't be the same on each side of the aircraft. It could stall at the wing tip first instead of at the root on this side of the wing. And at very high angles of attack, you might have more lift on one side of the wing than the other. And the aileron on one side would be more effective than on the other. And they call that asymmetrical lateral control, and it occurs at or near stall angles of attack when a stall strip is missing. Now let's take a look at a wing generating lift, and this is a magnificent Boeing 747 with smoke generators on the wingtips to show you what's happening to the air around the wingtips. Now, we said earlier, when a wing is producing lift, there's relative high pressure underneath the wing and relative low pressure on top of the wing, and what happens is the air actually tries to make its way around the wingtip to destroy the lift on the top of the wing. They call these wingtip vortices, and one of them is called a wingtip vortex. Well, the air actually does make its way around the wingtip, and it does destroy lift on part of the wing. So some of the lift is being destroyed out at the wingtips due to these wingtip vortices. So if you were an aircraft designer and you wanted to eliminate or at least reduce these wingtip vortices and reduce the drag that they cause, they decrease lift and increase drag. Well, one way to do it would be to put a real long high aspect ratio wing on the aircraft like you have on that beautiful glider we saw earlier. Well, the problem with a high aspect ratio wing on an airliner is it would be very, very structurally difficult to do, and it might be heavy and it'd be hard to make it strong enough. So there is a very simple, elegant way to solve that problem, and that is with what is called a winglet. Now, a winglet is installed on the wingtip like so, And here it is on a Airbus, on a Boeing 747, it goes up. On an Airbus, it goes both down and up. But what it does is interfere with the flow of the air around the wingtip, and it minimizes these wingtip vortices, and therefore you do not have the loss of lift and increased drag that you would have had. So the desired effect from these winglets is to increase lift and reduce drag, and so they increase the lift-drag ratio. Now, they're going to ask you on the test, do winglets reduce the aspect ratio? Well, no, they actually have the effect of increasing the aspect ratio, and they'll also ask you whether they optimize dihedral and improve lateral stability. No, that's not what they're there for. Winglets are there to increase the lift-drag ratio. Now let's take a look at another concept they want to ask you about, and that is wing dihedral, and that's when the wing tips are bent up like this. The purpose of dihedral is to give you increased lateral stability. And what that means is if you get down on a wing, if one wing of the aircraft goes down, the aircraft will start slipping in that direction. And when you have dihedral, the airplane slips towards this wing, and this wing, which was bent up, is now level, and it has more lift than this other wing, which is now even higher. So the down wing tends to get more lift, and that tends to right the airplane back up again, and that's dihedral, and it increases lateral stability. Now let's talk about two more concepts. One concept I hate and another concept I love. And the concept I hate is work. We're going to talk about that. And the concept I love is power. And they are related to each other. What is work? Well, work is done, according to the FAA, when a resistance is overcome by a force acting through a measurable distance. I'll bet we can make a formula out of this, so let's you and I do that. Work equals force times distance. We're going to use the formula W equals F times D. Work equals force times distance. Now let's take a look at a way that they're going to ask you a question about this on the FAA written exam. They're going to say you have this 120-pound weight and you want to lower it from a table to the floor, and you're lowering it by 3 feet. And the question will go like this. The work input required to lower, not drop, a 120-pound weight from the top of a 3-foot table to the floor is how much work? Well, work is force times distance, so we're taking 120 pounds and moving it 3 feet, and we're still having to have that, even though we're letting it down, we have to have 120 pounds of force on this weight all the entire time we're letting it down. And so the force times the distance is 360. 360 what? Work is expressed in foot-pounds. It's 360 foot-pounds, and that's how much work we accomplished in that particular case. Well, now that was a relatively simple question. Let's take a look at a more complicated question they're going to ask you about this. And here you have a situation like this. You still have 350 pounds, you still have 3 feet, but now you got some 12 foot in there. Let's take a look at the question. Here's the way the FAA will give you the question verbatim. An engine that weighs 350 pounds, there it is removed from an aircraft by means of a mobile hoist. The engine is raised 3 feet above its attachment mount.